Okay. And that's time. Just take what you have. Time. Time's up. It's amazing how demolished these things can look in just 15 minutes. They crumbled up with blood on them. Correct answer was negative 207.
I forgot to subtract.
I was off by 1.
So we'll see. I mean, I'll have to grade them, okay? Everyone understand what was required there? Antiderivative. Once you do that, you use the condition to find out what C was. Antiderivative again. And I made it so that all the numbers worked out nice, so that you should have nice integers. So, okay, I'll grade those. I'm not going to go through it and post the solution up here. If you struggle with that, you can talk to me, office hours or something. All right, so what were we doing last time?
Substitution.
Substitution. We had just started the idea of substitution. So before I get too far into this, I want you to be aware that we talked about this notation last class. Right, we talked about this notation. That's the notation we use to let you know that we want you to find the general antiderivative of a function, right? So in your homework, you might notice that in the next few sections, you're going to see sometimes there are some numbers there on the top and bottom of that symbol. So you might see something like this. All right, you might see something like that. And we have not discussed this. So in the homework, if you see a problem like this, I want you to ignore the numbers and just find the general antiderivative here of, in this case, it would be x squared. The only drawback to that is that if you try and check your answer in the back of the book, it's not going to look the same, all right? So if you watch my homework solution videos, that'll show you what the answer should look like, all right? So we will talk about the numbers. We're just going to talk about those later. All right, so we discussed this idea of substitution, which is the real first technique that we try in order to find antiderivatives, other than like the general kind of power rule and things we know from Cal 1. And this was kind of the set of steps I told you to take. Look at the integrand, right? Look at the thing you're trying to find the antiderivative of. Within the integrand, you're looking for something, some expression, and then you're also trying to find separate from that expression the derivative of that something. So it should be like this game where you're trying to match things up. And once you find the something, whatever it is, and its derivative, you want to make sure that the derivative of that thing is free. Okay, so it should be in the numerator. It shouldn't be trapped inside a parentheses or a square root or something like that. If it is, then you need to try to find a new something. And then I also said that it is all right to be off by a constant. So we did, I think, 1 or maybe 2 of these, and pretty much the rest of today is going to be doing more examples. All right, so I'm going to put some problems up here, and we're going to see if we can come up with the substitution. So I'll just pick a few out of the book to start us. And then we'll start making up our own. Yes?
I'm sorry, it is super hot in here. Is there any way we can make it a little bit cooler?
I'm not sure I can control that. There's a thermostat on the wall, but I don't have any control.
On top of the tricycle, are those like the domain or something?
Yeah, that'll mean something to us later. Yeah.
They're like where the antiderivative falls between, right?
Yeah, it's going to have geometric implications, which once we get to it, it'll make perfect sense. For now, just act like they're not there. Yeah. Yeah. I mean, I can walk up to that thermostat, but I can't do anything to it. So, yeah.
Right, I just didn't know if there was a way.
Yeah, I don't have an easy way. I could maybe try and call facilities. Let's see if it gets any better in the next 15, 20 minutes. If you feel like you're going to pass out, let me know. Okay, let's do this one. Should we start out with something pretty basic? Yeah, let's do something pretty basic. All right. Christian DeLuna?
Yes.
Where? Christian. Okay, so you're in front of the firing squad first here. So when we look at this, right, we want to first rule out things that, like power rule. We want to rule out things from Cal 1 that we've seen. We want to rule those things out first. So can you somehow rewrite this so that it's just, x to a bunch of powers, like on the quiz where you have some, separated terms? Or is this too complicated to be able to kind of split apart? What do you think on that? I mean, can you split this apart? You would have to do like 2x over the entire denominator plus 3 over the entire denominator, right? That's the most you could do, but then at that point you can't simplify that. So you're pretty much stuck, which means you go to the next thing, which would be substitution. So now I need you to look at that, and I need you to try and see something within there, and I also need you to be able to see if its derivative is there also. So do you see something in there that if we take the derivative of it, we get something that's in there still?
2x plus 3 would be...
2x plus 3 is what?
So like x squared would be the... the antiderivative of 2x, right? And then 3 would be the derivative of 3x.
Okay, so you're seeing that the derivative of x squared is 2x. Derivative of 3x is 3, right?
And then
So
negative 7 would just...
derivative of negative 7 is 0, right? So if the entire denominator, right, the whole thing, if that's the something, right, then its derivative is actually right there on top, isn't it? And so you see something, you see its derivative. Is the derivative trapped inside of a root or inside of a parenthesis or anything? No. And the derivative is in the numerator, right? So I think we have it. But let's just rewrite it so that we can really kind of see. This will be helpful later. I'm going to rewrite it like this. Okay? All I did was slid the numerator off to the side. That's legal, right? I can do that. Now by doing this, I'm hoping that you see you have like 1 over something, right? And then times the derivative of that something. Yes? So once you're there, what do we do once we're here? Once we've found something and the derivative, we make the substitution, right? So what we do is on the side we say let u be equal to what? The something, right? In this case it's the x squared plus 3x minus 7. Now what was the next step after that? Differentiate that with respect to x. Okay, so from here, once we make the substitution, this is why they call it the substitution method. You make a substitution. We take the derivative of the left side with respect to x, and then we take derivative of the right side with respect to x, which you already said was 2x plus 3. Right? And then what was the next step that I did in class?
Solve for dx.
So I moved this dx to this side, didn't I? So I multiply both sides by dx. So I have du is equal to, in parentheses, 2x plus 3 times dx. And so this right here, I need to go try and look for that over there. And I also need to look for this and replace it with u. All right? So everything is first example. So everything matches up beautifully, doesn't it? So this right here, this is right here. So all of that's going to be replaced with what? Du. And then this piece down here, right there, is this piece right here, and that'll be replaced with u. So then we just rewrite the whole problem, right? So this becomes antiderivative, right? This is telling us, hey, we want to find the antiderivative of what now? 1 over u times du. Now, Max, where's Max? Max, what's the antiderivative of 1 over u? Natural log of u, right? Now, normally we put natural log of the absolute value of u. Okay, so that's a formula, but it should be up here. Max knows it, so it's natural log of the absolute value of u. And then we always have to put what there at the end, Max?
Constant.
Plus our constant. All right, so there we go. So from this step to this step is where you're taking finding the antiderivative, so there's no more integral sign, right? And we are there, but our answer is in terms of u. We need to get our answer back to in terms of x. So we just replace that u with that. Natural log, absolute value of x squared plus 3x minus 7 plus some constant, and we are in business.
That's cool, man.
That's it. That's the answer. So the idea here is that if I take the derivative of this, right, I should get back up there, which is exactly what would happen. You could check it. Derivative of natural log of something is 1 over that times the derivative of what's inside, so you get back that. Okay. So this one worked out perfect though, right? Like everything just fell right into place. So let's try something where it's maybe not as obvious and maybe things don't fall into place. Why don't we I'm just going to use the same problem. I'm just going to tweak it just slightly, okay? So instead of having on top 2x plus 3, what if we had negative 3x, no, not negative 3, sorry, negative 6x minus, hold on, I forgot what, minus 9, sorry. There we go. What if we had that instead? Over the same thing, okay? Mohammed?
Yes.
Okay, so on this one, Mohammed, you again would go through the whole process of making sure it's not something that you can do easily, right? And then you move on to substitution. And so do you see something and its derivative here?
No.
Not quite, right? So what's wrong? If you're choosing this to be your u again, right? Then the derivative of that we already know is 2x plus 3, and that's not exactly what we have up there, right?
Yeah, we can take the negative 3 as become a factor.
Yeah, so we could factor that out. So what would be valuable for us to recognize here is that even though negative 6 minus 9 is not the derivative of that, it's off by a constant. So if we recognize that the top, factoring a negative 3 out, would give us 2x plus 3 on top, right? Right? Sorry, I forgot my little dx here. So we'd have to recognize that, right? Okay, and now at this point, you have your something, you have its derivative up top, right? And it's off by a constant, but we said that's okay, right? Okay, so let's make the same substitution. Nothing over here is going to change, right? I'm getting ahead of myself. Okay, so do you see on this step where I take the derivative with respect to x, and on the next step I always move that dx to the other side? I'm going to stop doing this step, okay? I'm going to, from now on, go from here straight to here, all right? Just to save us one step. All right, so now we play the matching game. You know, this right here is going to be, what part of this? Just that part, right? That right there is this. And then the part on the bottom is our u, right? This right here is our u. And then what about that constant, that negative 3? What about that part? Just leave it there, okay? Because remember, constants always come for the ride. So if I rewrite this integral now, Jace, you're up. How is that integral rewritten then, in terms of u?
1 over u.
Okay. What about this? You're hibernating over there. Okay, what do you got?
You could still do 1 over u, but instead of the 1, it's the -3.
Yeah.
When you bring it over to turn it to the derivative, you just do the -3 on.
Yeah, so we really have -3 on top of the u, and then we have du, right? That's what we really have, instead of 1 over u du. The -3 is really not relevant. In fact, you could pull the -3 completely out of the integral because it's a constant, okay? You can only do that with constants, put them out front. You can never take variables out, all right? Only constants. So I'm going to say -3 times whatever this is, and we already know that that's natural log. So -3 natural log absolute value of u plus c. And then last step would be to replace u with all that stuff up there, and we'd be done. Okay? So slightly different problem. I mean, just a slight tweak, but there is an impact on the answer, right? All right, let's try something else. How about this? How about sine of the square root of x over the square root of x? Jacob. Where's Jacob? Jacob's up. All right, so first you run through and make sure it's not something you can do without substitution. So, you know what the antiderivative of sine of x is, but this isn't sine of x, right? Sine of root x over root x, and we definitely can't cancel those, right? You do that, and what happens? You laugh, but someone, that's bad. All right, so we're not doing that. So substitution. So do you see something in its derivative? Root x, that's your something. Okay, so let me write that down. U is root x. Okay, what is the derivative of that? 1 over 2 root x, right? 1 over 2 root x. And then dx. So remember I said I'm going to skip that part. So I take the derivative of this and then I put dx on the end. I'm just going to do that every time. Now, do we have that over there? So how could you rewrite this? Like if I forced you to do this, to rewrite that as sine x times something, what would come next? Just rewrite this. I'm forcing you to take that sine x out front. So what's still over here? 1 over root x, right? 1 over root x dx. Everyone see that? It's just, all we're doing is manipulating this algebraically. We're not doing any math, so to speak. So now is it a little easier to see that we're pretty close to having this, right? Like this is our sine, this would be u, right? And this is almost du, isn't it? It's almost du. What's different between this and what's over here? The 2, right? Like if this 2 wasn't here, they would match perfectly. Yes?
Does it matter if the constant's in the numerator?
Nope. It just is, if it's off by a constant, that's all that matters. So what we're going to do now is we're just going to play a little game. We're going to make this look exactly like that. So we don't want the 2 here, right? So if I don't want a 2 here and I have a little equation, I can just multiply both sides by 2. So if I multiply this side by 2, and this side by 2, then my left side becomes 2 du, and my right side becomes, the 2's cancel, exactly, right? It's exactly this now, isn't it? So Erica, right? Where's Erica? Erica gets to tell me what the rewritten integral is going to become. So integral, okay, so what is this going to become? Sine of u. Okay, so this is sine u times 2 du. Okay, now Erica, what can we do with the 2? Move it to the front, right? Let's just get it, rip it out of the integral completely. This 2 is not inside the sign, right? It's just a factor. So just pull it all the way out. And now, Erica, What's the antiderivative of sine of u? So we have a 2, right? We have a 2 also out there, so that's going to come along. And you said it's negative cosine u? Okay, so negative 2 cosine u. Remember, you have to have the negative because the derivative of cosine is negative sine, so you have to make it switch back to positive. So negative 2 cosine u, and then always remember plus c. And last step, because we're not done, right? Replace u. What was u? Root x plus c. So if we take the derivative of this, we should get back this expression right there inside. That's what we should get. Yes?
So on some of the homework problems, what I was doing was in order to solve for, I would solve for dx by dividing both sides by whatever.
You can do that.
Was its, in for lack of a better term, constant.
Yep.
It eventually does the same thing with
Yes.
just a little bit more writing.
Mhm.
Is that acceptable in most regards?
Can I show what you're suggesting? Okay, so one thing that has been brought up here is that there is another approach to this. So let me just show it to you. If you like it better, that's fine with me. I have no problems as long as you get the right answer. Here's how it's done. So I guess maybe you would have gotten it to this point over here. Is that safe to say?
I'd leave that
Leave it up here. Okay, just leave it there. All right. All right, so over here, at this stage right here, okay, you just took the derivative like this. Okay, everyone paying attention? This is what's being suggested. dx just isolated over here. Solve for dx. So that means I'm going to multiply both sides by 2 root x. Multiply this side by 2 root x. Yeah, anywhere you want, man. 2 root x. And then they're gone, right? And then what you have here is 2 root x du equals dx. Yep. And then now, just plug this in for dx into this integral. So if I do that, I get sine root x over root x times, what's dx? 2 root x du, right? I'm doing what you're, okay, everyone see that? And now these root x's cancel. And what you're left with now is integral sine root x du, yes? 2, yeah, sorry, the 2. Let me just pull the 2 out. And then what? What would be your next step?
Substitute u.
Substitute u to be root x, right? Or root x is 2. So that right there gets replaced with u, and you get du. And that's the same place we were at before. Yes? Okay. That is completely okay with me if you do it that way. All right? I'm not going to tell you not to. Here's why I don't teach it that way. All right? So I'm just going to explain why I don't do it this way. There's a couple of things involved here. First of all, I never, ever like to write integrals where I have 2 different variables in the expression. Okay? I don't like having x's and u's within the same expression, especially when I've replaced something with u. Like u is something, I mean, there is a connection between u and x, but I think this just to me is dangerous. That's just my personal preference or personal opinion on that. The other part of it is that I think it's less what's the word I'm trying to look for? I think there's less thinking involved with this. If you actually just go here and you go, oh, I'm just going to solve for dx, plug in, and then algebraically move down until it's simplified, then I will replace this u with this. That's not like a higher level of thinking. That's like just substitute and go and see what happens. I think when you do this and you're trying to match and see patterns, I think that is better off for a student long term. Does that make sense? As for what we're doing in this class, look, we have to move away from the idea that everything is going to be a procedure we follow. And a lot of it's going to be instinct and just trying to see things. So that's all. I just think it's, whatever. We'll do another one. Okay, here we go. Many Cal 2 professors teach it the way you're describing. So it's not wrong, it's just yeah, not my preference. Okay, let's try another one. Let's see if I can't hang y'all up on something here. Okay, that's interesting. How about this? 4x squared over 1 plus x to the 6th dx. Did you read what I wrote on your little? Oh, I didn't hand them back. I didn't hand back those quizzes about you, right? Oh, I have them. I replied to your stuff. Oh, sorry. No. Let me go ahead and I'll just pass those around now. This has, you know what I'm talking about, the little thing, information thing that you gave me? So on these were interesting. I mean, if you filled it all out, then I gave you full credit. But there were people who like just left a bunch of stuff blank, and so your grade might reflect that. So it's a pretty easy A, pretty easy 100. All you had to do was answer a few questions. So, all right, you're up. Sorry, Luis.
Yep.
Got to find something in its derivative here.
All I'm seeing is the x to power
X to what?
x, well, x squared and x to the 6th.
Okay. You play baseball? You ever play baseball? No?
Ooh.
How do you hit a ball? How do you hit a ball in baseball? Stand there and then what do? You swing, right? So you got to swing. So try something. You're going to have to try something for you, right? Would you agree? Okay, so this one is not so obvious maybe of what the substitution should be. And I will concede that. That's why I put it up on the board, all right? So let's just go with some. Can we rule out the fact we cannot split this up, right? Like we can't do 4x squared over 1, 4x squared over x to the 6th. That's algebraically wrong. So we can't do that. So the only other thing we have right now is substitution. So step up and take a swing. Just give me a U. I don't even care what it is.
Yeah, I'll check the 1 plus.
The whole denominator. Let's just go with it. Okay. So now the reason why this doesn't seem like it's going to work is because the derivative of that is not there, right? So let's just look at what the derivative is. Derivative of this is 6x to the 5th dx, right? You don't have 6x to the 5th. You're off by more than a constant, aren't you? You're off by 3 factors of x. So this doesn't look like this is going to work, right? Does everyone understand why we're kind of jammed up right now? That's a baseball term too, I think. Jammed up. Like I think when they pitch you in. I'm not a big baseball person, but isn't that called jammed up?
I think so.
Yeah.
I think jammed up's also like a law enforcement term for jamming up a cop for doing something wrong.
I've never heard that one.
Watch Blue Bloods.
Hey, maybe your method of solving for dx will work here.
So it'd be 1 over 6x to the 5th du equals dx.
Yeah. Maybe. I'm just saying maybe. I don't want to go down that road, but maybe it would. Yeah. Okay, so what do we do? What do we do when we take a look at that and it doesn't look like it's working? You got to maybe try something else, right? Anyone have any ideas? I'm going to put or here. Maybe there's another substitution we can do. What? Maybe we can what?
It looks like maybe the 1 over 1 plus x plus, or 1 over 1 plus x to the 6th is almost like the derivative of tan inverse somehow, or tangent.
This is almost like the 1 over 1 plus x squared.
Yeah.
right? Because we have that thing that we've all memorized, right? The antiderivative of 1 over 1 plus x squared is obviously arctangent of x, right? So you're recognizing that already. That's good. We want to be at that point where we're kind of seeing this is almost there. But this would have to be something squared, right?
Yeah.
Well, maybe it is.
Maybe x to the third.
Maybe, yeah, it is x cubed squared, isn't it? Okay. Now, if you look at it this way,
Oh, man. Dang, man.
if you look at it like that, is it still the same expression? Right? Now do you see something in its derivative? What is the something? Gotta be careful here. What is the something in its derivative? I don't see arctan. There's no arctans in here. The something has to be right in front of us here.
Yeah, x to the third.
X to the third.
And then x squared.
Look, x to the third, if that's u, then what's the derivative of this? What's the derivative of this? 3x squared. What do we have? 4x squared. We're off by a constant. You all see that? So I'm going to go for this. X cubed, right, is my u. The derivative of this is 3x squared dx. Okay, so this we tried swing, strike, right? And then what was your name? Stephen. I'm not sure, Stephen, why you did that or how you did that, but that was nice because you recognized this might be arctan of, like this might work out to be an arctan antiderivative, and then you said, well, that would have to be something squared, and then, oh, there it is, right? It's looking like this might lead us there. This, look, everyone, this is the part of the class that's hard to teach, okay? I can't just say do step A, B, C, D. You have to like see things, and everyone's at a different place with that. But you have to swing, right? You have to try things. You have to manipulate it. You have to, keep going, keep going, keep going. All right. So I'm gonna kind of mess with this still. We know that x cubed will be replaced with u. We have 4x squared dx. Over here we have what? 3x squared dx? We'd really like it if this were 4x squared dx, right? So is there anything you can do on both sides of this equation to make this a 4 and not a 3? Multiply both sides by 4/3. 4/3, right? Just hit this with 4/3. Hit this with 4/3. Over here the 3's will cancel, and voila, you'll have your 4x squared dx, right? 4x squared dx. And over here, well, you have 4/3 du. We don't really care about that because the 4/3 is going to get pulled out of the integral anyway. We don't worry about it. Y'all see what I mean? I mean, this is different. It's not like calculus 1. You have to think about this. All right, rewrite time. Ricardo, where's Ricardo? Okay, Ricardo, I would just like for us to rewrite this expression now, all right? So in terms of u, you okay with that?
Yep.
Okay, so what do we got?
1 over 1.
1 over 1 plus u squared, okay? And then this part right here is going to be replaced with what?
We could put the 4/3 on the outside.
Yeah, so 4/3 du, okay, and you're going to pull the 4/3 outside and slap your du. Now, Ricardo, why are we happy to see that now? Yeah, that's one of the antiderivatives we should know. I put stars next to it, right? That's arctan of u. So this just becomes 4/3 comes for the ride, arctangent of u, and then plus our constant, right?
Sorry, what happened to the 4x squared?
This is 4x squared right here.
No, over on the second line.
This one?
Yep.
What happened to it?
Yeah. Like when you rewrote.
I went from here to here. No, I went from here to here.
Right.
And then from here up to here.
Right.
So I replaced x cubed with u,
Right.
and I replaced 4x squared dx with what was 4x squared dx? 4/3 du.
I see.
So the whole thing kind of just vanishes out
I see.
and becomes the 4/3 du. So to answer your question, this is what replaced. It got replaced with this and this. Okay, almost done. Replace u with x cubed. 4/3 arctangent of x cubed plus c. Okay, if we take the derivative of this, we should get back the original problem. If you like puzzles, this is kind of like puzzle, like it's kind of a brain game. You got to come up with something. Here's the good news. When you're doing your homework for chapter 5, section 5, you know you need to use substitution. Here's the bad news. When we get to a test and you have 5 different things that you could do that we've spent time on, you don't know if it's substitution or integration by parts or trigonometric substitution or partial fraction decomposition. Then you're sitting there, you're looking at the problem going, what do I do, right? Like what do I try? And that's what makes it really tough. All right, so right now we have a very narrow field of view. We're just doing substitution. It's when we broaden it that it becomes harder. Does that make sense? Because you might spend 10 minutes just trying to figure out the right method, and then can you execute the method? Not trying to discourage you, I'm just trying to prepare you for where we're headed, all right? Okay, let's do another one. How about this one? This is one of my favorites. So if we look at what we've done so far today, first problem, substitution was just right there in front of us, right? U du, no problems with it. We did another example where we were off by a constant, but the substitution was pretty clear. Next one we did was a sine root x over root x. That one was a little kind of tricky, but we knew that the derivative of root x was 1 over 2 root x, so we were able to figure that out. The one I just did really wasn't obvious. It took a pretty big realization that that x to the 6th could be visualized as x cubed squared. This one, the substitution just doesn't seem like it's going to get you anywhere, but it does. So Jeremiah, where's Jeremiah? Yep, Jeremiah. Batter up. Something in its derivative. Can you? You can do whatever you want. That's what my dad always told me. You can do whatever you want. All right, so you want to go with u is 2 plus x. All right, what's the derivative of that? 1. So I'm going to write 1 dx. I don't need the 1, but that would work. So do you see the derivative of this somewhere? Do you see 1 dx here somewhere? Right here, right? So you have 1 dx here. You have u, right? The only thing you haven't accounted for here is this x up front, have you? So maybe there's something we can do here. So this is going to become something with the u in it, right? This is going to become just du. And our goal is to get everything to have u, right? So can you tell me what x would be in terms of u? So look at what you wrote down over there. Right?
U minus 2.
Yeah, look, solve that for x. If u is 2 plus x, then what's x? It's u minus 2. Just subtract 2 from both sides, right? So if we do that, we should be able to rewrite the whole problem. So let's rewrite it. I'm going to stick with it because so far it's working, okay? So what do I replace x with? No. U minus 2. I need that in parentheses, right? Because it's 2 terms. Keep going. What's this? U to the 30th. And what's dx? du. Okay, so there we are. There we are. That is all legal, okay? That's all legal. You came up with the u, du, you solved for x, you rewrote the problem. Now your problem is in terms of u. The question is, can you solve that problem? So here, why couldn't we solve this problem? Why is it that we couldn't find the antiderivative using any shortcuts? Like, could we have used the power rule? You know that rule that we had about x to the n, finding the antiderivative? We couldn't do that because we had this x out here, right? Could you have multiplied 2 plus x times itself 30 times? Right? Expanded it, and then pushed that x through all those answers? So you'd have this huge expansion, right? And you could do them each one at a time. But who wants to do that, right? So is this any better? This is key, everyone. Is this doable compared to this one? Why? Yeah, because all you have to do is distribute this here and this here. Why can't we push this x in here and here? I mean, you can't do it, right? You got to do the power first. And nobody wants to expand 2 plus x. But here, with rewriting it, I can now push the u through, and now this becomes u to the 31st minus 2u to the 30th. Like that, right? And now, Tatum, can we do that? This is doable, right? So this is kind of like what your quiz was just on. This is like x to a power, so you can just use your power rule. You ready? Okay. So Tatum, what's the antiderivative of u to the 31st power? Antiderivative, yes. So what happens to the power? Power goes up or down? Up, right? So it's going to be u to the 32, but you have to have something out front, remember? So 1 over what out front? 32. Okay, so the antiderivative of u to the 31 is 1 over 32 u to the 32. And then minus, let's just bring the 2 along, 2 u to the 31, right, is the power here? But then you have to divide by 31. So 2 over 31 u to the 31 plus some constant. Almost there. Replace u with 2 plus x. There it is. That is the antiderivative of x times 2 plus x to the 30th power. That means if we take the derivative of this, right, we should get that? So look, this example is an example where you do a substitution that doesn't necessarily look like it's going to get anywhere, but it actually does get you there. So again, that's that whole idea of take a swing, because it might actually work. Questions on that one? Let's see, you all passed Cal 1, right? Okay, so let's take the derivative. Here we go. 2 different terms. Derivative of this, chain rule. 32 comes out, right? 32 cancels with that 32. So all I'm left with is 2 plus x to what power? 31. Okay, minus. Here, 31 comes out, kills off. So I'm left with the 2, and then 2 plus x to the 30th. By the way, notice I did not take derivative of what was inside because I know it's 1 already. So when I did this, I did chain rule. Derivative of the inside is 1. So, okay, now, is that the original problem? Okay, so let's do this. Let's factor out a 2 plus x to the 30th power. What happens if I pull that out of here? What am I left with? I still have a 2 plus x here, right? If I pull out 30 of these, I'm still left with the 2 plus x. Okay, if I pull out 30 of these, what am I left with here? Minus 2. And then what happens if 2's cancel? And so you have x times this to the 30th, and that's the original thing. Okay, so nobody in here is going to look at that and be like, oh yeah, that's 1/32, 2 plus x to the 30. I mean, that's just, we have to have a systematic way, right, of going back to this. That's what the next few weeks is about. Giving you things that you can't find the antiderivative of mentally and trying to get to this. All right? And then later, we'll see why. Why would you ever want to do it? More? More? I can feel you begging for more. This, I told you last class, I think, substitution is the easiest of the approaches we're going to be doing, but it's foundation. You have to do this to move on. You have to, substitution is the base of the pyramid, so to speak. All the other methods are useless to you if you can't do substitution. All right. I like that one. Yeah, maybe not yet. Batter. I didn't like baseball as a kid. Octavio? How's it going?
Good.
Is this making sense? Can you appreciate the challenge of it? Like, it's definitely not as clear and cut as everything maybe has been up to this point. All right, well, let me just make sure you understand this is 1 over x times the cube root of natural log of x. So that's not x cubed, that's cube root, okay? Maybe I should pull this x a little further out like this and put it times there so you can see it. All right, so you're up, and you get to pick a u. So you're looking for something in its derivative there.
I'm gonna go with the cube root of ln of x.
Cube root of ln of x. I absolutely am so happy you did that. It's wrong, but I'm happy you did it. But it's important for us to see why it's wrong, okay? All right, so you're going with that, all right? Let's just see what happens. You have to take derivative of this now, right? And the whole idea is that the derivative of this should be somewhere over there, because we need to see something as derivative. So let's rewrite this. Cube root is the same as 1/3 power, right? Okay, so now let's take our derivative. We have chain rule here. So if we do chain rule on this, first thing that happens, 1/3 comes out, right? So 1/3, then we have natural log x to what power? Subtract 1 from that, so negative 2/3, right? We're not done. Times derivative what's inside? 1 over x. And we're done with the derivative, so dx. Okay. So Octavio, let's look at this. You called this thing right here, you called that u, right? So the only thing left in the problem after we've used that for u is 1 over x dx, right? So if this is your something, its derivative needs to be here too. But its derivative is this, isn't it? It's all this stuff. You do have part of it. You have this part, right? But all this stuff is like too much. So the problem is you grabbed too much for your u. The cube root of natural log of x was just too much. Does that make sense? So you step back and dust your, what do? They always take so long at the plate, right? Sit there, right? You watch baseball, they sit there and, they'll call time, right? Walk around. So you get back up and okay, so you're trying, you strike 1. So what else? You grab too much on that one.
Can I use ln of x?
You can do whatever you want. Okay? But it needs to make sense to you why this is going to work. This one's going to work, right? Because there's your ln x. Do you see now its derivative is there? 1 over x dx, okay? So now du is 1 over x dx, and now you can play your game, right? You can start matching things up. I'm going to rewrite this over here. I'm going to rewrite it this way to really illustrate kind of yanking that x from the front and sliding it to the back, separating it completely. And that might help us see it, right? And it matches perfectly, doesn't it? Like 1 over x dx, this piece right here. That right there is this, right there. And this piece right here, you know, it's hot and stuffy in here. I think it's all the brain power in here. That's what it is. So,
Everybody exhaling.
yeah. Shit. Okay, here we go. I'm going to keep going with you, Octavio. What? Hold on. Octavio. Oh. Say it. Octavio. Octavio. Okay. Wait a minute. Hold on. Octavio. I'm going to try my best. I know I can say it. I just don't know if I'll remember how to say it. Octavio. How is this going to be rewritten? That's u. This is du. So our next line should have just u's in it.
So it's going to be 1 over
1 over
cube root
cube root
u
u.
times ln of x.
Oh.
I mean u.
Nope.
1 over u.
This right here is this, right?
Yes.
Which is du. Okay? That's it. You're here. You're on base. Okay? Let's see if Gina, let's see if Gina can, bat you in? Maybe I do watch more baseball than I realize. Maybe I do. I seriously only watch it when it gets to like the World Series. That's it. That's the only time I ever watch it. Maybe I watch it too much. Okay, so at this point, can we do anything with that? My hint is yes, you can. And my hint is also, we've done this already a few days ago. So this right here, 1 over u to a power, right? That's really u to the 1/3. And then can you bring it up? There you go. So that's really just u to the negative 1/3 du. And now you have your power rule, right? We know what the antiderivative of u to the 1/3 is? Because that was like 2 classes ago. This is going to be, so negative 1/3 plus 1, right, is 2/3. But out front you have to have 1 over that, so it becomes 3/2 u to the 2/3. Then your constant. So this from here to here, I'm expecting everyone can do that at this point. It may not be super fast, but it can't be 5 minutes. I mean, it has to be within like 30 seconds you can get that, I think, at this point. And now replace u with ln of x. Any questions? The way I write this, be careful. ln x to the 2/3 plus c. Okay? That's it right there. Now also I'll mention that 2/3 right now, there's this like log property where you can pull powers out front. This power can't come out front. The reason why is because this power is acting on the entire expression. If it was acting just on the x, then it could come out. So we can't simplify that. We're just leaving it just like it is. All right, that's it. Good. How do you think you get good at this? Practicing hundreds of problems. All right, you ready? Secant x tangent x. Times secant squared secant x dx. Christopher. Chris. I'll give you a second to write that down. So one option when you're up to bat, I guess, is you could just step into the pitch, take a hit batter, take a base. I think they get you if you do it intentionally, though, right? Like if you just like step out and get hit, it's your fault. They won't let you go on base. So, all right. Let you kind of simmer with that for a second.
So would you be secant x?
Would it be? Is that what you want to do?
Yeah.
Why do you want to do it? I'm going to put it here because you're taking the swing. Here it is. But why that?
Because the derivative is secant x.
Yeah, because the derivative of secant x is secant x tangent x. And you have it right here, don't you? This problem actually, even though it's written all, see all this stuff, it's actually not that bad. Am I stretching that too far to say that? Like this is easy. I'm not saying that, but I'm just saying it's not that bad. So the derivative of secant x is secant x tangent x and then dx, which you have. You have secant x times tangent x times dx. It's all right here. dx, secant x, tangent x. And then what part's being replaced with u? Just the secant, right? The secant here is going to be replaced with u. So Chris, when we rewrite this, what's it going to be? Secant squared u, and then everything else is du. And do you know what the antiderivative of secant squared is? Tangent of u plus c. And just replace u with what? Secant x. There it is. Tangent of secant x, right? Tangent of secant x. This is not, be careful, this is not tangent, we're not saying it's tangent x times secant x, right? Like that, it's composition. It's tangent of secant x. Questions on that? Yes?
Question, could you use tangent for the second part, like times secant squared, or would that just be too complicated?
Wait a minute. Could you use what for the second part?
For the secant squared part? Yeah.
I'm not sure I follow you.
Secant x, could you use tangent for that part, or?
I'm still not following you.
You're saying for secant x, tangent x, you can use secant x, but then when you get to secant squared, can you sub that for tangent instead?
Is that what you're saying?
Yeah.
Can you replace secant squared with tangent?
Yeah, use that as your u, or instead of doing.
Oh, okay. I see what you're saying now. The question here is, I think I know what you're saying. Could you have used tangent x?
Yeah.
Then the derivative of that is what? Secant squared what?
X.
Okay. And what do you have up there? Do you have secant squared x?
So no, you couldn't use.
That's right, you can't, because this is not secant squared x. This is secant squared secant x. If this was secant squared x, then absolutely you could have used u's tangent, and there's its derivative. Then you would have had to deal with that, right? But you see why now?
Yeah.
Okay.
Thank you.
All right, good question. All day long, we could just do u sub all day long. See if there's anything else here. It's kind of popping out at me. Oh, yeah. Yeah, I like that one. Boys like that one.
Seems like you're about to play a trick on it.
Okay.